sort of more impromptu talk of some preliminary results of my project at the PIBBSS Fellowship with Simplex, specifically Adam, Shai, and Paul Riechers. And yeah, I just wanted to show the first results of the analysis that I have, and maybe if you have some ideas of things based on that, to let me know. The general thrust of the project was that we're trying to understand language models, or large language models eventually, in terms of very simple models, in this case hidden Markov models, or weighted finite state machines equivalently. This comes from, my background is in formal language theory, so there's the Chomsky hierarchy of formal languages, which has regular languages at the bottom, context-free, as a superset, then context-sensitive and recursively enumerable languages at the top, which can be computed by Turing machines. Eventually, we'd like to know if LLMs can be Turing machines, but for now, we're even still struggling to make LLMs learn toy tasks that are regular, so this is maybe a bit away. Let's quickly go over the formalisms that correspond to these hierarchies. So regular languages are languages that can be accepted by finite state machines. So you have a finite set of states, and then labeled transitions between them. And those can be seen as a very, very simple language model. If you put weights on the arcs and make them normalized, then you can generate symbols based on a state that you're in. You start in state 1, for example, and then you generate an A or a B. You move to the corresponding state, you can generate more symbols. This is a very simple way to define a very simple language model. As the name suggests, it has finitely many states, so it's not... Well, technically, this corresponds to how large language models work as well, because if you have finite precision, then the language model can also have only finite states, but we normally assume that the continuous state spectrum is large enough that we can say it has almost arbitrarily many or infinite states. And we often approximate the activations and transformers as real numbers rather than finite precision floating point numbers. But yeah, this is a simple language model that we can use to approximate what a large language model could do. At the next level in the formal hierarchy, if we have a finite state machine that also has access to a data structure such as a stack, so a stack where you can push things onto the stack and then the last thing you pushed you can pop again, that gives you the context-free languages, which used to be the model of human language for a long time in linguistics, until people showed that, for example, in Swiss German, this isn't enough. You actually need context-sensitive languages, which is even one level higher. So a single stack doesn't suffice, but for most parsing algorithms that were used in classical NLP before transformers, this was the model of choice. So yeah, one level above finite state machines. And then, yeah, at the last level, if we have a finite state machine and then some memory in form of a tape where we can move left and right, so we can't just access the last thing that was pushed onto the memory, we can move around and select individual things. If we bound the size of the memory in terms of the length of the word, then we get the context sensitive. If it's linear, then we get the context sensitive languages, and if it's unbounded, then we get the recursively enumerable languages. So basically an unrestricted Turing machine, the formal model of a computer if you didn't have memory limitations. Okay, so as I mentioned before, basically you can model any process as a finite state machine if you say that you don't have finite states but infinite states. So instead of saying we have a stack where we push things on, we can just say we move into another state that corresponds to a specific stack configuration. The same can be done with tapes as well. However, it's much harder to describe a system in terms of states than in terms of a stack or a tape, because a Turing machine, we can just describe the actions that it does based on what it currently sees in memory. If we wanted to do the states and the memory together in finite state machine form, we would have to define one state per configuration of the memory and then define the transitions individually for all states. which gives you a much, much larger description length. So that's why these aren't just formal distinctions, but actually also correspond to something more real in terms of how easy is it for a finite or bounded number of parameters to prescribe this formal system. So yeah, here for example, if we're counting occurrences of a certain symbol, we could do that with a stack, or we could do that with a finite set of states, or well, with a set of states that grows as the number grows. Where am I going with this? I think this will become clear in a second. I wanted to go from the computational mechanics view, where we look at things as Markov models that can be either finite or infinite. But in both cases, we look at the set of states and we look at the transition dynamics between them, but we don't really model it as a set of states plus an additional data structure. And so this project was more about can we go beyond looking at transformers as the states and the transitions between them, but actually model data structures explicitly in the mechanics of the transformer. So it turns out that there has been a lot of formal analysis of what transformers can and can't represent. They can't even properly represent finite automata at arbitrary lengths. However, they're very good at approximating, like if you get a large enough transformer and give it enough data, it can approximate things even beyond weighted finite automata up to a certain length. And the reason behind that is that for a given length, you can always model it as a machine, as a finite state machine. And so the question is it just doing that, or is it actually explicitly modeling this additional data structure that allows it to potentially generalize and use much fewer parameters to do the same thing? Yes?
So the first statement, transformers with finite. Why is it first?
This would take a longer time to explain than we have here, but I can point you to some resources. Will Merrill has a lot of work on this. For example, David Chang, Michael Hahn. Basically, you always make some.
Actually, I misread transformers as transducers.
Oh no. Transducers can represent finite automata perfectly. They're more powerful, or exactly as powerful actually. Okay, belief states. I think we probably don't have to go into this because we've heard many talks here about computational mechanics. The main idea is that we can represent where we think that the underlying finite state machine of a data generating process is, like what state it's in, as a distribution over the states. And that by definition lies on a simplex. Like any distribution can be modeled as like any finite distribution can be modeled by a finite simplex, where we have coordinates in a coordinate system that have to sum to 1. So if we have 3 coordinates, then we get a 2D structure, this triangle here, and any point on that triangle has coordinates that sum to 1. And that gives you these beautiful pictures of fractals that have been used in papers at Simplex to show belief distributions of processes that give rise to fractals if you have a non-deterministic process. So if you have a process where for a given state you have multiple ways or multiple next states for the same symbol, then you can get fractal belief structures. And so this is sort of what we're looking for also for these higher level formalisms, or like context-free languages. We would also like to see belief state geometries and look at those and interpret them in the same way if possible. So yeah, so far this work works very well if you have a finite state machine or a finite HMM. Then you get this finite simplex. So for 3 states, for 4 states, you can do this for any number of states. However, as I mentioned before, if you go beyond the regular languages, you get infinitely many states. And so the question then is, what do we actually use to represent the states there, or the belief states? In the limit, you get an infinite dimensional simplex. That's sort of hard to work with, and also it's not clear how a transformer would work with that. If we have a model dimension of, say, 32 or 64, how does that model like an infinite simplex? Because when we do PCA, we want to actually reduce the dimensions of the model to get the simplex representation, but we would have to blow it up into infinite dimensions. But as I mentioned before, these data structures help you to model an infinite process with finite means and some potentially arbitrarily loaded data structure. So that's what we're looking for instead. Yeah, the deeper questions: do transformers approximate non-regular languages through the nearest finite automata representation? So do we always just, because in any data that we get will always only require finite states to model. We can always take any data distribution, because the data is finite that we feed the model. We could model it with a very large finite state machine. So one valid hypothesis would be, okay, the transformer just takes that data distribution and approximates it as well as it can using a finite state machine. Or does it use the data structures directly, which would require fewer parameters? Yeah, the toy problem that I looked at in this project is that the problem of parenthesis matching. They're called the DIC languages. So basically valid matchings are those where you have open parentheses before any closing parentheses. So every closing parenthesis has to be open before. And the specific setting here is that we're doing a language modeling task, so we're not, in the past this problem has been investigated by just giving a transformer a complete sequence and saying, is this a valid sequence? Which means that not only can it never have seen a closed parenthesis that wasn't opened, but also it has to close all the ones that were opened. So we have to return to a fully closed state. Here in language modeling, it's actually nice to only look at subsequences that are valid. So we don't ask, were all the parentheses closed again? We just say, is the sequence up to now valid? And if so, give us the next symbol based on that prefix. So if we've seen some open ones, some closed ones, and then more open ones, we accept this as a valid sequence, and we just say what would be the next token distribution given what we've seen so far. And for simplicity, we just choose the open probability to be the same as the closing probability, which is just a half. So if the sequence so far has been valid, and we are not in a fully closed state, then we can open or close with the same probability just by a coin flip.
What's invalid? What would be invalid?
Yeah, if you start with a closed parenthesis, it will be invalid. So in the beginning, you always have to see an open parenthesis, and then once you've opened it, you can close.
And but if you see more closed ones than opened ones, it's also invalid.
Yeah. Exactly. So this can actually be reduced to a counting problem. You have open parentheses that represent the count +1, and then closing ones that are -1, and you're never allowed to go below 0. So in the beginning, you always start with 0, and then yeah, you're just counting. So these are basically numbers, plus and -1. That's for the task where you have DIC languages with only one type of parentheses. You can actually vary the number of parentheses. So if we parameterize it by n, we can say n is the number of pairs of parentheses that we allow. And then the second parameter, which is very important, is that do we bound how many parentheses we can open before we force it to always close? And that's a way to make this infinite state problem into a finite state problem. So yeah, here n is the number of types and m is the maximum nesting depth. There's an example of, yeah, we don't have to get into it, but like it's annotated with the depth at each step. If we have only one type of parentheses, then it's, as I mentioned, it's just a counter. So here we have the states of a infinite state machine, where we always start in the fully closed state, and then we open a new parenthesis with probability 1, and then from here we can either open or close with a probability Q1, Q2, and so on. We've set this to a half for a toy task here. This is a figure from another Simplex paper. If we say that we have more than one type of parentheses, we cannot just count anymore. We actually require a stack, because it's not just about how many parentheses were open before, but if we also have to keep track of types, then valid nestings require that if we close, that type was the last one that was opened before. So we have to go back in memory and remember what was opened which type was opened last, and this is very naturally a stack. However, if we want to just look at counting tasks, we can reconvert this back into a counting task by saying we only care about the number of parentheses that were open, but we don't care about the very correct nesting, and that is in formal language land that's called scaffolding. And then we just look at how many types of parentheses do we have, and then we can just maintain that many counters to accept the language perfectly. The finite nesting depth assumption is an important one, because if we impose that, then we always have a finite state belief representation. If we only have one type of parentheses, then that number of states grows linearly with the nesting depth. If we have more types, then it grows exponentially. Okay, so what does the literature say so far about this task? This has actually been studied in depth. One paper that I particularly like by Dr. Mishra and Navin Goya in 2020 showed that counting languages are actually, counting is a task that transformers are surprisingly good at. They also show formally that counting sort of doesn't fit neatly into the Chomsky hierarchy, because it covers some non-regular context-free languages and some non-regular context-sensitive languages. However, it doesn't allow you to do the Dick language with more than one type of parentheses, which is also context-free. Yes?
Sorry, I should probably miss this. What is FSA stand for?
Finite state automaton.
Oh, okay.
Yeah, sorry, I'm using 3 different acronyms for the same concept. Finite state machine, finite state automaton, Markov decision process, hidden Markov model if we don't see the states. Yeah, I should use the same acronym for everything. So basically what they found was that not only do transformers learn this language very well, they also learn to generalize languages that require counters. So if you train on sequences of up to 50 and length up to 50, and then test on languages up to 150, transformers are very good at generalizing one type of parentheses and even 2 types of parentheses if we shuffle them. They, however, found that this worked only if they got rid of positional encodings. So the only thing that they use to keep track of the position is causal masking. And then there's more recent work that also looks at the proper task of multiple types of parentheses. And there they found that if you fix the nesting depth, then it can also learn to generalize, transformers can learn to generalize that language as well for sequence length, but they can never learn to, or in their experiments, they couldn't learn to generalize nesting depth. And also, in order to make that work, they used very special, very unrealistic custom positional encodings, which is often a trick that is used in empirical experiments for formal language theory with transformers to make things work. With recurrent neural networks, you don't need that, because they don't need positional encodings to know what happened before, because they're recurrent step by step. But transformers, because they can be trained in parallel, they need positional encodings to keep track of the order of the context. Yes.
What do you mean here with special custom? Like it's some relative position encoding?
Yeah.
Like
just ones that aren't normally seen in actual language modeling training.
Like, why can't you just use like a sign-based, like, relative, like, is there a specific reason?
Yeah, they tried it and it didn't work. Basically, that's they didn't say, like, they found a construction where hypothetically, if you set the weights in a specific way, and if you set the position encoding in a specific way, then it perfectly recognizes the language, and so they also used that position encoding for training to see that it also worked. There's no particular reason that should be the only way that works. Mm-hmm. But when they tested normal common position encodings, it didn't work. We don't have that much time anymore. I wanted to give a quick demo of what we found so far, which was specifically for the task of one type of parentheses. So let's look at the experiments. We look at those that are representable with finite states. So we fix both the number of parentheses to 1, and we fix the nesting depth, but we look at different nesting depths to see how it develops and how to extrapolate when it goes to infinity. And we always start in a fully closed state, so this is the normal assumption that we described before. And then the steps are we make a hypothesis about what the activations will look like if we assume the transformer models the HMM version, so not using some clever data structure, but just using the HMM. And then we train the transformer on sequences, perform PCA on the activations in the residual stream, and then compare our hypothesis to that. The expectation is that if we model these finite depth sequences as finite state automata, then we need exactly n plus 1 states for a nesting depth of n. So if we have a nesting depth of 3, for example, we need 4 states. And then that would mean if we look at the simplex, or if we project it to a simplex, in experiments at Simplex, the company, it was shown that if you just do PCA, it automatically aligns it with a simplex. So that's what I was hoping to find in the activations. And then it would look a bit like this, where you just have the activations cluster around the vertices of the simplex. Because if you start in a fully closed state, then it's always determined which state you go to next, based on the symbol that you see. And this is in fact what we saw in the beginning when we look at a nesting depth of 2, which corresponds to 3 finite states. We see a triangle, and on the vertices we have the states. So this seems to confirm the hypothesis. Now, if we go to deeper nesting depths, we would expect the number of PC dimensions required to cover the variance to go along a straight line, because it's linear, right? The number of states that you need to represent finite nesting depth grows linearly with the nesting depth. However, this is not what we saw. Instead, it actually stays fixed for 99% of the variance, in almost all cases, is covered with just 2 dimensions. And this is a surprise. The question was then, what's going on? Does this mean that it's not actually modeling these states as separate? Is it in fact just modeling the next token distribution, which in our setting there are only 3 different ones of, regardless of how many states the HMM has? It's not actually directly what's happening. So I wanted to quickly look at some activations together. Right, this is the wrong one. Yeah. So here's a visualization of the activations in the transformer trained on the parenthesis matching task. And the different colors here correspond to the different nesting depths. So if you align it in just the right way, then you have like nesting depth is 7, 6, 5, 4, 3, and so on. So it's actually counting somewhat along a line. However, there are a lot of other lines and there's a lot of noise happening. So the question is, what is that coming from? And if we look at only a couple of positions, it becomes a bit clearer. So basically what we have is, we have two tracks here. One track gives us the even counts, and the other track gives us the odd counts. And the reason for that, at least why I think this is happening, is that we have a very strong positional dependence in our task. If you think about parenthesis matching, like the first one always has to be open. So at position 1, we always have a count of 1. And then we can either open again, bring us to 2, or close, then we get back to 0. So at even positions, we're always at an even count state. So we actually have these two tracks corresponding to even positions and odd positions. But even with that, there's still a lot happening. So I've now looked at only 2 different positions, and this allows us to get only this one track rather than this more filamented tracks for each individual odd position and even position. But even here, we still have these many elongations in the cluster. So long story short, what we found was that these all correspond to different histories that result in the same count. So if we have open, open, close, close, or open, close, the balance is 0 both times. However, because we have position encodings, we can differentiate between them, and so we get 2 points that are slightly distanced from each other in the cluster. They're still clustered correctly, but they're not just 1 point. So the clear next step is what happens if we remove position encodings. And this is what we get. It looks very pretty and a bit more orderly. Here we again have all the positions, but they're along very clear lines, so they're only elongated in one direction, in one dimension. And here, the reason I think that we still have multiple lines for multiple positions is that we can still differentiate positions because we're summing a different number of previous tokens in the softmax. But if we look at only 2 positions here, sorry, this is a live demo, 10 to 12. Yeah, then we get this. So here, basically, for every state in the, or for every nesting depth, we get exactly 1 point. Not exactly, because we still have 2 tracks. And again, this is, well, yeah, this is the even positions and the odd positions. But as I said before, the positions also correspond to the nesting depths. So we have 1 point per position. So actually, the position encodings give us a bit too much fine-graining. The transformer can distinguish histories that should be equivalent, but it doesn't quite learn to completely separate them. However, if you get rid of position encodings, then you get these very clear lines. And this is also something that explains why in experiments removing position encodings helps with counting tasks, because it doesn't have all this additional information that it doesn't need anymore. Yeah, I think we're at time. So, yes.
Sorry, I missed the part of why did you not think it only uses 2 PCA dimensions rather than needing more and more?
So it's not actually, it's using 2 PC dimensions. In the last layer, it's using a bit more than 2 dimensions. In the first layer, we have 2-layer transformers. But basically, the idea is that when we're doing this counting task, the counting happens along a line. So we don't actually the transformer finds a more efficient way of distinguishing the states than putting them at the vertices of a simplex. Instead, it puts them more or less along a line, like these two lines, but it can linearly separate for each position.
And you originally expected that it would be a simplex just because that's the state and that was just the first thing you thought of? Or?
So, I mean, that as a simplex was shown in experiments with other processes at simplex.
I mean, sure, you mean like in totally different time models that do different things? Or?
I mean, not that different time models. I mean, they're still very close in the number of states. Actually, no. The MES 3 process, for example, has 3 states. So maybe this is actually the point that if you only have a few states, then the simplex representation is something that arises naturally. But if you get into like 10 states,
I mean, I would have more thought it's in at least in the other toy models I've seen from simplex, usually you're not always sure that it's 100% probability this state or 100% probability that state or that state.
Yeah.
That's why you want a vector space to represent your uncertainty.
Yeah.
But here,
So
you're right, it doesn't even have that, so why have like a vector
so
space?
actually we did some experiments where we made it not quite sure what state it is in. So it had ambiguity for most positions in what state it is. It still recovered exactly this line. But it wasn't full ambiguity. Like, we didn't say we don't know at all in which nesting depth we are. We just said you could be in nesting depth 0 or 1, 1 or 2, 2 or 3. But basically if you make it completely arbitrary where you are, so you do a stationary distribution of all possible states, you're saying in that case you would expect it to find something like a simplex because it has to. Is that what you're saying?
No, not what I meant. But
Sorry?
that's not what I meant, but let's just move on.
Okay. I think we are over time already. So let's discuss it in one-on-ones afterwards. Thanks.